So lastly, let's return to the phase diagram of nitrogen. So here it is. And so nitrogen has a phase diagram that you'll see looks a lot like that of water and carbon dioxide before it. There's a solid phase, a liquid phase, and a gas phase. At low enough pressures, actually, nitrogen also has a situation where the solid phase transitions directly to a gas without a liquid phase. But there's this big liquid phase, which is the part at 1 atmosphere that gives rise to liquid nitrogen. Now, one thing that we can do with this, which is we can ask whether or not if you actually cool liquid nitrogen, if it actually becomes a solid. And this is something that actually can also be done experimentally. It's a little bit difficult to cool it because, but as an easier way to go about it is to actually decrease the pressure of the gas around the liquid nitrogen. And so now this is another demonstration that we want to show you.
So liquid nitrogen is very, very cold. It is so cold that the most convenient scale to use is the Kelvin scale, absolute temperature. And in Kelvin, liquid nitrogen is 77 Kelvin. In centigrade, it's minus 196 degrees Celsius. Liquid nitrogen has to be stored in a vacuum flask. This is basically a giant thermos bottle. And when I pour it, at room temperature, it's a boiling liquid. It's as if we put water into a red-hot skillet. And so this nitrogen is just going to boil and boil, going from liquid to gas, and that's about it. But if we change the pressure, we can change the phase of the liquid nitrogen by cooling it, it turns out. And so in order to change the pressure of in order to change the pressure above our liquid nitrogen, I'm going to use this vacuum system, and specifically I'm going to put a beaker full of liquid nitrogen under the bell jar, and then I'm going to pump on it. As the liquid nitrogen evaporates, it takes with it the heat. Even at 77 Kelvin, there's still heat in that liquid nitrogen. And as it evaporates, the heat goes off with the gas, and the liquid that's left behind gets colder and colder. And at some point, we're going to get below the melting temperature of nitrogen. And hopefully, we will see solid nitrogen. So, on top, we have an aluminum block with a rubber top so that the bell jar will seal against the rubber. The holes are where we're pulling the air. This plexiglass shield is to keep us safe in the event that the glass bell jar should break. Now, this is a big old roughing pump. There's a motor, drives a belt, and turns a vacuum pump. The vacuum pump is pulling gas through this tube. This chamber is a cold trap. We don't need to use the cold trap because we're only pumping on nitrogen. If we were pumping on water, water vapor would mix with the oil that the vacuum pump uses, and it would turn the oil into an emulsion, which would no longer pull a vacuum. It's one of the easiest ways to ruin a vacuum pump, actually. So from the cold trap, we have a line that goes to a valve, and the valve is right under the bell jar. And so after I turn the pump on, the other thing that I'm going to be doing is turning this valve and throttling the vacuum so that I'm not pulling it too quickly. This is a very strong, fast pump, and it's fairly easy to sort of overdo it and get everything splashing up on the inside of the bell jar. We do have a couple of indicators. We have a rough vacuum indicator. This goes from 760 torr, which is atmospheric pressure, down to 1. So this tells us in a rough fashion what our vacuum is. And after this reaches 1 or below, we then turn to this indicator, which is telling us millitorr. So this starts where this leaves off and goes all the way down to what is essentially a high vacuum. So what I'm going to do is I'm going to take the bell jar. It's called a bell jar because it rings. That's actually also a test for structural integrity. If there were a crack in this jar, it wouldn't ring as nicely, and that's one of the tests that I do on vacuum jars and also beakers. So in order to keep moisture from condensing on the outside of the beaker, I'm going to start by filling the beaker with nitrogen. Inside a bath of liquid nitrogen. And what that does is it keeps water vapor from getting to the outside surface and freezing on as a frost. Okay, and that's the sound of the beaker getting down to the temperature of liquid nitrogen. And I'm going to do this. First, I'm going to turn on the pump. And quickly and start pulling the air, pulling the nitrogen now. So the nitrogen is boiling now because the pressure over it is lower than its vapor pressure. And because it's boiling without a heat source, the only heat, it's internal heat that's causing it to boil. It boils, it cools, and then what we see is solid nitrogen. The boiling liquid below is pushing the sponge of solid nitrogen up. And now you're among the few people on Earth who've ever seen nitrogen in all three of its forms. Everybody sees gaseous nitrogen every day, or everybody doesn't see gaseous nitrogen every day, but you breathe it as part of air. Liquid nitrogen you see if you've gone to a science museum. They break a rose by freezing it in liquid nitrogen. But solid nitrogen, the only way you can get it is by pulling a vacuum on it and allowing the temperature to go down to the freezing point by evaporative cooling. So we've seen it, but can we touch it? Let's do the experiment. Just have to lift up a weight. There's a vacuum in there. That means about a ton of atmospheric pressure is pushing down on this. There's no way I'm going to be able to lift this. The only way to lift this is by equalizing the pressure. And I can equalize the pressure by venting the bell jar to the atmosphere, and the moment I let any air in, there's enough heat in that air to melt the solid nitrogen back into liquid. So solid nitrogen is something that you can make, something that you can look at, but it's nothing that you can really ever touch. As the hissing stops, that means the pressure is equalized. And what we have is a beaker of liquid nitrogen.